Get out of here, Mr. Kerr. Mr. Kerr is trying to creep on me. Hi guys, so congratulations on your project. Mrs. Ling and Mr. Gearhart and I are so proud of you. So now it's time to kind of catch up so that you can be ready to come back to class and kind of know what we've been talking about for the last couple months. So to start with, we are going to be looking at particles. So there's this particle model for everything on Earth, basically. Everything is made up of particles. And these particles, we can't see them. You'll be reading more about them, but they are basically just another word for atoms. So everything is made up of these small particles. We're using the word particles for right now. Gas particles are freely moving. They move in straight lines. They bounce off of each other. They move very fast, about 670 miles per hour. And they will bounce off of something and keep going, kind of like bumper cars, bouncy balls. There's a lot of analogies that we came up with in class. So try to think of an analogy for yourself that you can use to keep gas particles straight and understand them. So air particles, it's a mixture of gases, mostly nitrogen and oxygen, argon, carbon dioxide, and hydrogen and dioxide, which would be water. Just to give you kind of a ballpark about how tiny these particles are, 1 cubic centimeter, so we're talking really small, 1 cubic centimeter of air, I'm trying to get it so you can see it in the video. Oh, okay, there we go. 27 quintillion air particles in that small little space. So very, 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 very small particles. Now you can't see me. Oh, there I am. Okay. So why can't you push the particles until they touch? If I have them trapped in a syringe, the reason that I cannot push the syringe all the way down is because those gas particles take up space, and they have spaces in between the particles. So if you want to try it out, there's a simulation on the FOSS-Web, which you know how to get to from the last video, or you can come into my classroom and I have a lot of syringes that you can feel around with. So that's gas particles 101. Main ideas about gas particles: we know that they can be compressed, they can be forced, compression, they can be forced into a small space, and they take up space, and there's spaces between the particles. So, moving right along, you are reading in your green book, and those pages are on your video note-taking sheet. Other things that can be compressed, other phases of matter. There aren't any. Only gases can be compressed. Water and also solids cannot be compressed. And again, if you want to see me try to compress some water, I have a syringe in my classroom. So, moving right along here through my notes, we know gas particles are always moving. They have kinetic energy, so the more kinetic energy that something has, the faster moving those particles are, so they might have more heat. The less kinetic energy something has, that means it's moving slower, and the less heat it has. So in order to increase kinetic energy, that is by heating something up, and that's called expansion, because those particles are going to take up more space. They're going to move away from each other. They're going to hit each other more often, and those particles are going to hit each other harder. So they will expand. And then the opposite will happen when something is cooled down. They will contract and come closer together. So that is the basics about expansion and contraction. All phases of matter, gases, liquids, and solids, can expand and contract, but only gases can compress. So that's something that I know you have on your video note-taking sheet that you can keep track of. Again, you're reading. If you would like to see some of the labs that we did, this lab right here on the screen right now, you can see we took this bottle of water, and some of the water came up through the tube, so we marked it at room temperature. And then we put the whole glass bottle into a container of hot water. So predict right now, what do you think happened to this water level when we put the whole glass bottle into hot water? I'll give you a couple seconds to think about it. What's going to happen? What do you think? Andre? Trevor? Brayden, what happened? You got it. It expanded. So those particles would warm up. They would heat up. They would need more space because they're moving faster. And so they would go up to the top of my bottle there. And look at my lovely drawing skills. There you go. Then what would happen if I took the whole thing and I would put it into cold water? What do you think? Tell each other. It would contract and those particles would come closer together. So then it would go down here and they would get closer together because they're not moving around as fast. Okay? Think about when you're outside. It's cold. You don't want to move around as fast. You don't have as much energy. Okay? So that's something to think about. So basically we made a thermometer in class. These are kind of how thermometers work in a little bit more detail, and you'll be reading about those. So expansion and contraction is kind of what we're talking about there with liquids. Moving on, I want you to kind of think about this situation. This student had a syringe filled with water, and some of the water dripped out after she had the syringe sitting in the sunshine. What happened? Go ahead and tell each other. Why is this student says that the syringe is broken? So is it broken or did something else happen? What do you think? Tell each other. I'm hoping and guessing that we said that it was expansion. Okay? Expansion, and then why? Well, there was an increase in kinetic energy. Those particles are moving around faster. They need more space. So there was an increase in kinetic energy there. Okay, moving right along. We are just blowing through this. Investigation 5 is what we're on right now. And Investigation 5 deals with energy transfer. So, when particles hit each other, there's going to be a transfer of energy. So when you're reading through on pages, I believe it is 32, I guessed it, 32 through 37. I want you to think about what happens when two different temperature or two different particles with different kinetic energy would hit each other. So let's say this is very, very hot, so it's moving really fast. This particle is very, very slow. It's cold, so it's moving slowly. So when they hit each other, they will then bounce off of each other and keep going in the same speed now because there is a heat transfer. Think about two situations from your life where you have experienced heat transfer. Think about maybe when you eat something hot or when you eat something cold. One big idea here is that there is no such thing as coldness. There's just heat. So heat can transfer, it'll transfer from hot to cold. So I want to bring up some of my main ideas here. And you may have come across some of this when you were doing your city planning. Some ideas about contraction, expansion. What if the maglev was in a cool climate? What would you have to worry about with the track? You would have to worry about expansion and contraction with that changing climate. So those are some practical things with your city that deal with the content that we were working in class. So important idea. Kinetic energy is heat. So if I have an increase in heat, I have an increase in kinetic energy. They are directly related. Energy transfers between particles when they collide. So if, like I kind of explained with my hands, if I have a hot particle and a cold particle, they collide, they will then transfer energy and reach equilibrium. Energy transfers always from hot to cold. So let's go at, say I go and I take a huge bite of cold ice cream. Well, the energy is going to transfer from my mouth, my body heat, to the ice cream. And so my mouth is losing energy to the ice cream. And that's what's happening there. And I would like you to come up with some examples of your own. So those are big ideas. We then did go into class talking about how to calculate energy transfer, which could be done with this equation right here. Calories equals mass times change in temperature. I am not expecting you to have to know that calculation or that equation, but just to let you know that you can find empirical evidence to support this idea of energy transfer, that hot things are going to lose energy, cold things are going to gain energy, and that there's an equilibrium there. Okay, guys, I think I blew through that very quickly. Again, I'm very, very, very proud of you, and you really pulled it together. I was impressed with how well you guys did, and you really did pull it together. So bravo, nice work. I can't wait to have you back in class. I know you're so excited. So work hard and ask me questions. I really did go through this fast, so let me know. Okay? All right. Bye.